When I began my career in 1987, I was primarily interested in solving fundamental problems in inorganic chemistry, particularly the design and discovery of new inorganic compounds with unprecedented structures and properties. Early on, my focus was on understanding structure-property relationships in chalcogenide compounds. These are important compounds that contain sulfur, selenium, and tellurium. We were aiming to create materials with novel atomic bonds, tailored electronic, optical, and other functionalities. This curiosity drove the development of exploratory synthesis strategies in my group that ultimately enabled the discovery and also design of over 1,000 novel compounds, laying the groundwork for breakthrough applications in photovoltaics, for solar energy conversion, thermoelectrics, for converting heat to electricity, and radiation detection for detecting nuclear radiation. Over the past decade, solar energy has been transformed by the discovery of a remarkable class of materials called halide perovskites. These materials are inexpensive to make, easy to process, and uniquely efficient at converting sunlight to electricity. When I began working on perovskites back in 2008, few believed they could compete with silicon, which has dominated the solar industry for decades. But in 2012, we demonstrated the first solid-state solar cells using a perovskite semiconductor, a discovery that helped ignite a global revolution in photovoltaics. Today, thanks to contributions from many other groups around the world, these materials have reached efficiencies once thought impossible and are now being developed for commercial applications. My group's role has been to design, synthesize, and understand these materials at the deepest chemical and structural levels. We discovered the compositions, solved the crystal structures, and uncovered the properties that make perovskites so extraordinary for capturing solar energy. Along the way, we developed lead-free alternatives, we pioneered stable two-dimensional perovskites, and provided the fundamental insights that have guided researchers worldwide. It has been tremendously rewarding to see how our early breakthroughs opened the door to a new generation of solar technologies, innovations that bring us closer to affordable, high-efficiency, and sustainable energy. Over the years, my research has opened new scientific frontiers and inspired innovations across diverse energy technologies. We also developed halide perovskite crystals that enable low-cost, high-resolution X-ray and gamma-ray detectors, now being advanced commercially through a company called Actinia. Equally important has been the impact of mentorship. I have had the privilege of guiding nearly 100 brilliant PhD students and more than 220 postdoctoral fellows, many of whom now hold faculty positions at leading universities or lead R&D teams in industry. Through their successes, the reach of our discoveries has expanded globally, driving innovation well beyond my own laboratory and shaping the future of material science. Of course, the work is never done. You will hear from us again.